And so I will share my screen in here. You can see it. Just confirm me, guys. You can see my page. Thank you, Ubeydullah Enes Şahin. Okay. And so section 5 is electromechanical system. Okay. So what's the electromechanical system? Electromechanical system is combining the electric and the mechanical system, but in one place or the one device. Okay, just the motor, electrical motor. Okay, and suppose that we have DC motor like the what this one. This is motor and so we have a rotor in here or rod at this time, and so maybe we have the spring factor in here with connecting or linking with the wall in here like this one. Okay, and so we have a friction factor in here Cm just like this one, because if we have a rotating the rotor or the rod, and then we have a friction, and we can model by using the what, the spring shape damping ratio just like this one. And so if we have this rod and this rotating part, and so we have the inertia. Okay, and also we provide the voltage value in here. It's in terms of the what, the EAT in here like this one, electrical voltage. And then we can drive this system into the specific points, positions, or the velocity value. Okay, but firstly we need to drive the what, the free body diagram in order to analyze these things, because it's a combination of the electric and the mechanical system. Just like this one. And so if we have this system, and then we have the armature current or armature resistance in here, and also armature what, the LA value, inductance value, and also if we have the rotor in here like this one, from due to the electromagnetic force we have the VBT value. Okay. And so we can drive the system in here. In the free body diagram we can model the rod just like this one, and so we have the torque motor T value in here, and we have the deflection of the angular position in here. Okay, and so how can we drive this system? We have the fixed field or stator value just like this one. This is the fixed field setup. Okay, this is the stator. This is the rotor. Okay, and so we apply the what, EAT. This is the input voltage. Okay, and so we have a current in here IAT just like this one. And then we can drive the whole the equation in here, and the first one or the first part is represents the what, the electrical current or the electrical transfer function, but the second part is the what, the mechanical one. Okay, and so we can combine it using the what, the transfer function domain or the Laplace transformation in order to represent the what, the EA as given to the what, to our system, which is known the GS plant, and then we will have the theta MS. Okay, this is the advantage of the what, the system dynamics. We can combine the two separate system, electric and mechanic, into the one form. Okay, system dynamic. So firstly, in order to solve it, we just solve to what? The electrical system. Just like this one. We have the input voltage EAT in here for given what to hold the system, okay? And so we have a IA current in here, okay? And so EAT times RA must be multiplied. This is consuming or the heat energy on this system. And then we have the inductance value. Just remember that we have the inductance and the IAT in the relation of these terms, DIA divided by DT. And then we have also VBT value, okay? This is the motor voltage in here, okay? And as we know the electromechanical system or the energy conversion course, we can write this thing VB is equal to what? The KB times dmdt divided by dt. Angular velocity is proportional with the what? The voltage B value, okay? And so this KB coming from the what? The electromagnetic equations or the simplification of these terms. And also we can write the torque MT is directly related to what? The KT times IAT. We can easily linearize the whole the system based on this information. This electromechanical system based on the electromagnetic theory can be summarized by using these terms, okay? And after that we can write the first equation in terms of what? The AS, which is equal to what? The IAS multiply with the RA times LAS plus KB, which is coming from this term. And so theta m s times s, okay? This is the first equation for the what? For the electrical networks, okay? So what about the second equation? Second equation is coming from the what? The mechanical analogy. Secondly, mechanical equations can be given by with the what? We have the torque value coming from or produced from the what? The rotor and stator, okay? And so this is consumed with what? The theta m dot dot times gm. This is the inertia or preserving energy of this form. And so we have the loss energy in here, just like this one, theta m dot, and we have the km value, theta m. This is spring factor connecting the wall, right? Km wall, and so we have the rotor value in here, Jm, and Cm can be given in here. Okay, and so in the second place we have the torque ms is equal to what? A theta m s multiplication s square jm, right? Cm s plus km. It's the basic representation of these terms, okay? And so using the what? Using the torque m is equal to kt times ia, and then ias can be written as the what? The torque ms divided by kt, okay? So what about this equation? Just remember the first equation, which is given in here, just like this one. We rewrite the whole equation using these terms, okay? And so we will have the AES value in terms of what? The torque ms divided by kt, right? Because this is the current, armature current value, okay? And so we can write the LAS value in here, and then we can add the KB times theta m times s, right? These are the equation. In the S domain, okay? And so this is expanding into the another form, AAS, right? And so we can write the theta ms time gm s square plus cm s plus km, right? And after that we should divide the kt because the torque ms is equal to the what? This term, right? And so this equation 2 is putting into the what? The torque m value in here, and then we can multiply with the what? Ra plus las, right? And theta m times kb times s. Okay? And after that, we just only have the what? The theta m value and EAS value. Okay? In the last form, we will reach to what? EAS is equal to theta m s in the parentheses of the what? The jm s square plus cm s plus km, right? And we have Ra plus LAS, right? And divided by KT plus KBS. This is the whole collection form for the what? For our algorithm. Okay? And so, how can I write the GS based on this information? And so theta m s divided by EAS. The interpretation of this equation is defined with the what? For a given voltage value, how much theta angle or position of the angle changed at a second or the one step in time domain. Okay? And so this can easily be organized in terms of the what? This equation, GAS square plus CMS plus KM times RA plus LAS and plus KT times KB times S. Okay? These are the transfer function for the what? For the whole motor equation. Okay? Any question? This just simple math calculation. Yes, Onur. Yes. Yes, we have a inductance in here, and then it's inside in the motor. So at every element in here, it's the stator and rotor. Just remember that, Onur, this RA is a rotor cable. But this rotor cable creates the what? The resistance of these terms. Okay? And this LA is coming from the what? Electromagnetic force, or the interaction between the what? Stator and the rotor. Okay? Just use this notion. The free body diagram just represents all the things in here. Okay? We don't have any actual resistance and the inductance value. Okay? So, any question? I will show this case, Mehmet Ali, because in the real application, I will use the sum motor in order to estimate the characteristics of the what? This RA and LA value in the next sessions. Okay? I build the motor, and then I will read the whole data using the STM32 board, and then we will measure the whole time the angular velocity of this motor, and then we will reach, or we will appropriate the proper transfer function to this RA and LA value. We will make the estimation algorithm in this lesson, but in real cases. Okay, Mehmet Ali? In the next sessions, we will talk about it. Okay. I will implement the motor application in the course of this lesson. So, just we don't have the at any time the LA or Km value. Spring factor cannot be included the motor because it's constantly rotating the around the the rod. Okay, and so this may be in simple assumptions km can equal to be the 0, and also LA is always small value, and we can reach to the LA is equal to the 0. Okay, these are the assumptions in here. At any case, we can use these assumptions, okay, unless if we are use the huge motor with the huge rotor coils and the stator coils. Okay, so if we are using the small motor like the DC motor, and then we can easily set that the LA is equal to the 0, Km is equal to the 0. Okay, and so the R system simplified to the this term, theta ms divided by EAS is equal to the KT and S square GMRA plus S CMRA plus KT KBS. Okay. In simple case, we can convert the whole thing. GS can be equal to the KT divided by S times GM RA plus CM RA plus KT KB. Okay, these are the simplification of these terms, and so this can be written in this formation. We can remove the GM and RA in terms of the if we divide the numerator and the denominator with the JM RA, and then we will reach the S plus CM divided by JM plus KT KB divided by JM RA. Okay, and so we can assign this term into the alpha, and we can assign the new variable in here k, and then our transfer function is equalized to the GS is equal to the k divided by S times S plus alpha. Okay, with to the k is equal to the KT divided by GM RA, and alpha is equal to the CM divided by JM plus KT times KB divided by JM times RA. Okay, just remember that this alpha is the time constant of this system. Okay, and so we can easily represent the whole deformation by using this notation, and then we can build to the for a given voltage how much our motor turns into the or around to the rod value in here. And so how can I prove that? We can build the MATLAB Simony model based on this information. Okay, so we should turn into the MATLAB application in here, just like this one. Okay, any question about these terms for starting? If you have any question, just speak it, or otherwise please shut up, because I will write the code. Okay, there is no question, and then we will continue with with these terms. Firstly, we need to give these terms in here, like this one. Okay, so we have the initialized motor, but we need to also give the initialize the motor parameters. Okay, so we have JM in here, for example 0.01. okay, and so CM 0.1, for example KM, or KM can be equalized to 0. Okay, and so we don't need to build these terms in here. Okay, and so the KT should be assigned with the what, the 1, for example, and KB is equalized to 1, for example, and RA can be equalized to 0.001, for example, and then we can build the R model. Okay, and so our system constants can be assigned with what the K is equal to the what the KT divided by RA times JM. Okay, and also alpha value can be given by CM, or this term can use the underscore in here for the common tongue. CM, okay, and this is the CM divided by JM plus KT times KB divided by JM times RA. Okay, this is the initial condition for the what for our parameters. Okay, and so how can I use or build the transfer function in here? And so transfer function can be assigned with these terms. Okay, DC motor or simplified DC motor can be assigned in here. We can use the constant value for the motor voltage in here, just like this one. EA can be assigned, and for example, at all time we give the 5 voltage in here. Okay, and so we can measure the whole values in here, but this is equal to what the theta m, or the position of the motor, but the which position? Angular position, right? These are the case. And so how can we build this numerator in here? And so this is equal to the K, and this is equal to the S times S square plus 1 alpha and 0. Okay, these are the shape, because in this case S times S plus alpha, S square plus S times alpha, right? These are the equation. Okay, and so if I run this code, and then under the wave voltage is applied to this system, to this DC motor, and then theta m is changed in time. Okay, and so if I examine or evaluate the scope 3 in here, and then this all the time, this degree is to what? 0 to 50 value in this case. But what's the dimension of these terms? This is equals to the what? Radian, right? And so how can I convert this radian value into the degree one? What's the formula? Just remember that. Please write this formula, because I don't remember just now. We should use the gain in here. Okay, and so this gain must be multiplied with the what? The radian value. For example, if we have the 2 pi, and so we reach the what? The 360 value at the 2 pi, and so I think this formula must equal to the what? 180 value divided by pi. This correct or not? If it's true, please tell me. Okay, thank you, Onur, for your contribution. And so if I run this code and then we will have the change in degree of these positions. Okay, and so at all time we will have the 3000th degree at the what at the 10 seconds, but it's not useful information in here because in the DC motor we always check or control the velocity values of these terms. So how can I assign the velocity of these terms? Just remember that if we have this nomination and then we can take a derivative values of these terms. Okay, this is the angular position in here, just like this one, right? And so how can I obtain the derivative values of this term? There are two ways to build this nomination. We can use just this block in here, just like this one. Okay, this the radian dec sec. Okay. Or we just add the what the another term, this the degree divided by sec. Okay, and so if I rerun this code and then we will have a velocity, angular velocity values of these terms. Okay, and so we have this value like this one. We have 286 degree divided by second velocity at this time. Okay, and so at 1 second we are constantly closing to the what, the 1 degree, our var notation in here. Okay, so this is the one way, but the another way to taking derivative of these terms is equals to the what, to this one. We may not use this information in here. Okay, but we can add the some other coefficients in here, k times a's. This produce to what, to derivative values or the velocity values of these terms. Okay, and so this angular position is equals to the what, the angular velocity value. Okay, and so this is equal to what, the radian sec, right? And so and radian 1 divided by sec and radian 1 divided by sec, but this is the degree one, sec. Okay, and so how can I check these terms? And so we can add the mux value and so this must be equals to the what, this one. If this is true, and then we will have the same results in here. See, we have the same results. Our both plots are on the same page in this scope. Okay, so for a given voltage, and then we can derive the what, the some basic notations in here, right? Because if we have the 5 voltage and we apply this voltage to this motor, and then we will have the what, the degree seconds value of the what, the 300, around the 300 degree divided by second velocity values of this term. Okay, but in real life application we have the some special case or the a different way to set this motor velocity value, which means that we always use in the microcontroller as the what, the timer or the pulse signal to emulate these systems. Okay, for example, if we have this nomination in here like this one, okay, And so this voltage can be created with the what the MATLAB function. Okay, but this MATLAB function produced what the pulse in here. Okay, pulse modulation. This just kind of the timer interrupt relation in the microcontroller systems. Okay, and so we have a clock in here like this one. Okay, and so this clock provides the time formation in here, just like this one, and so we generate the EA based on the what the some conditions. For example, just remember that we have the what the PWM with the duty cycle and its frequency values, right? And so we can use the T mod value in here like this one, the mod T, and this T should be equalized to the 1 or the frequency values, but the 1 divided by frequency value, because this frequency value, for example, if it's equal to the F is 10 Hertz, and so we can generate the pulse at this frequency value. Okay, and so if we have this information, and then we can add the frequency or frequency values of these terms in terms of the constant value in here, just like this one. For example, 10 hertz can be used in this case. Okay, and so also we can generate the T mod signal in here. For example, if we are using the 1, and so this T mod is always produced 0 to 1 value. If I choose this F 0.1, and so we have the 10 seconds period in here, and so at all the time we have this period, and so if we have this information, and then the R half period can be equal to these things. Okay, and so at each case EA int value, for example 5, we have 5 voltage in here, and then EA int should be equalized to the 5 value, and otherwise this EA should be equalized to the 0 value. Okay, and so in the last case EA should be equalized to EA int. Okay, and so in order to understand how we can accomplish this algorithm, we should give the scope of these terms. Okay, and so if I run this code and then we will have the pulse signal in here. Okay, for example, we have this signal in here, but in the we have this nomination in here. 5 volt voltage is given in here at a period of 10, because the 0.1 is at 10 hertz, and so the R period 0.1, and so the half of them is 5 volt and the other part is the 0 volt. Okay, but there are some missing points in here, just like this one. And so how can we remove this effect? This is the solver error, and so we should set the model configuration parameters in here, just like this one, and then we should select the fake step in here. Okay, and so 1 E minus 4 or 0.1 millisecond should be utilized in the in generation of these terms. Okay, this directly relates to the solver error, and so if I run this code and then we will have the time response in here. Firstly, just remember this EA is in real life application is not finite. I'm sorry. I'm sorry. Yes, fixed steps. No. Apply. If we rerun this code and then we reduce the number of the iteration time in here. And so it's highly slow at this time, and so not finite solution in here in the pulse modulation, because the EA int and KF in 0. Okay, should utilize the different approach in here to produce to this one. I think it's the solver error, but this couldn't be singularity solution. But the fixed steps we need to give this one max step size less than given at this time. Okay, and so we need to return to the variable step in here. This directly relates to this transfer function utilization. If we have the MATLAB simulating function just like this one, and so we don't have the n error. This is continuous time formation, but this is the second discrete time domain, and so we will not have the finite domain or the not finite solution. May happen in this case, but in the next case we will build this function in the what the MATLAB function domain. Okay, and so at this time we will have this nomination just like this one, the 0.1 0.1. okay, at this case, because in the voltage value we will reach this nomination, but it's not useful for this case because we should build in this case. I'm sorry guys, but we need to give this domain in the MATLAB simulating formation. Okay, and so we will rewrite the whole equation in here. Just like this one. And see, theta ms and es can be built with what the k s plus alpha. Okay, or k s square plus alpha s. Okay, and so theta ms times s square plus alpha s, which is equal to the what, the EA k. Okay, and so in time domain we should give the what, the theta m dot dot plus alpha theta m dot should be equal to what, the EA k. Okay, and so theta m dot dot should be equal to what, minus alpha theta m dot plus EA k. Okay, these are the formation of the what, the R solution. And so if we are using this nomination, and then we can build the what, the new MATLAB function body for this one. Okay, so just I copy of these things in here just like this one, and so the any other terms is commented through. Okay, and so just need to what, the MATLAB function in here in order to build this function. And so we should give the what, the EA as an input, and theta m and theta dot m should be produced to the what, the theta dot m. Okay, so and output and theta m dot dot must be equal to the what, the alpha times theta dot, right, minus alpha çarpı theta dot m, right, and plus EAK, right, plus EA times K, right, and so the K and the alpha must also given to to this equation. Okay, and so we don't have this variable in here, just like this one, and then we can create the motor function body, and EA can be considered in here, and integrator value should be given in here because this is the theta dot m, and also we should give this one, and so K and alpha value is defined in the predefined function, right? K must be assigned this term, and alpha must be assigned these terms. Okay, and so we can easily analyze the scope value of this thing, right? And so after that we can push the model configuration parameters in here. Okay, the fixed steps. In 4, and so if I run this code and then okay, alpha what's wrong with this code right now? There are some other problems in here, guys. One value cannot be read in here. Wait, I don't understand what this parameter is coming here. Apply. This EA can be used in here. Is this equation true in here? EAK, yes, S square, alpha square, yes, it's true. Okay. I'm sorry, guys. In the first code you will have these nominations. You understand these things in here? We have the algebraic group because at the upper side of this code we don't have any connection, but we have the MATLAB function. Okay. Error tolerance. Okay. We just designed our terms in here for the KT and RA GM value. Firstly, GM should be smaller than these things, and so CM smaller in here, and RA is coming here, and so we select the wrong parameters in here, I think, because we don't have any solver error in here right now, but the JM or the RA is increased in here because we have the oscillation in here, I think, and so we don't have enough parameter to complete this text. Okay. And so after that we can say we'll these terms in here just like this one. Okay, and so if I rerun this code Okay. See, what's the problem in here? Problem is that we don't have any actual value for these parameters. For example, the CM, JM, KT, KB, or RA is not appropriately selected by our algorithms. Okay, and so our algorithm cannot solve this equation because our solution is going to the infinity value. Okay, these are the problem for this case. But in this time we have this information in here. Okay, and so we have at this time, just see that 0 velocity and the 5 velocity is going in here because we have the theta dot m. This is the theta dot, right? This is the velocity value of this term. And so how can I increase this value? By using the higher constant frequency value. For example, 100 Hertz timer value is applied to this signal, or the pulse is applied to this section in here. And then our system, how can be affected from this nomination? And so just see that in this case we have this pulse style signal in here, just like this one. See, at the end of this code we have the 2.5 steady state value of these terms because we increase the timer frequency in here for the pulse modulation, and then this pulse modulation is higher than our state response in here. And then if we apply the 5 voltage with the PWM values of the 50%, and then this yields us to what? To this system. From the 0 we have the 2.5 degrees second velocity value at these terms. Okay, and so this is why we should use at the motor drivers to the 1 megahertz driver, motor driver for the step or the DC motor, or we just use the transistor with the higher frequency value to drive the system to the specific values of these terms. Because if we have the 100 Hertz in here, just like this one, and then if we drive the electronic motors or the motor driver with the frequency of the 100 Hertz, and then this velocity cannot be achievable at this case. In physical applications. Okay, and so we have, see that we have some oscillation in here, but the 1.8 and 3 degree divided by second is happening in here. Or we can give the 100 values in here, just like this one, but in this case 5 is applied in here with the ratio of these terms. Thank you, Onur. And so how can we add the duty cycle of this code? Please, at the next case, in the next week, please try to solve it. How can I add the duty cycle in here? Because if we add the duty cycle in here, and then we just think that we have the motor driver in here, step motor or the DC motor. Okay, and so this motor driver is used with some basic frequency with 1000 Hertz. Okay, and so if we had this Hertz, and then we can select or we can drive the specific points of this motor velocity. Okay, this is how we can achieve to our controller system in order to what? In order to represent in the domain of the PWM signals. Okay, because in the microcontroller we just only use this timer as a in terms of the frequency of this timer and the duty cycle of this timer. Okay, so if there's no question, that's all for this week. The next week we will continue with the time domain application, but please just read the book section that I have talked about in this lesson and review the whole information in here. Okay guys?